Okay, we go to next topic, low frequency response in BJT amplifier. Okay, the source capacitor, okay, CS, and the coupling capacitor, CE and CC, will determine the low frequency. Remember, you have to remember this all the time. Okay, during low frequency, the capacitive reactance, XC, is decreased when frequency is increased. Okay, this is like that I show you before, 2 pi f c. Okay, 2 pi f c, x c is decreased when f is increased. Okay, the capacitor will act as a low resistance element. Okay, so the general low frequency equation is 1 over 2 pi RC. Now, 2 pi RC, for this one, F, also the FL. L is for low. Okay. In this example, I use voltage divider with bypass RE. It's used to determine the break frequency or the cut-off frequency. Okay. Then, these frequencies are used to determine the overall response and the lower cut-off frequency. Okay, I want to ask you, how many frequency we will get during the low frequency response for the voltage divider? Okay, remember that all these frequency comes from CS, CE, and CC. So we have 3 frequency. Okay, 1, we have FLS, this one FLE, and this is FLC. Okay, so these 3 frequency will be calculated using this formula. Okay, and these 3 frequencies will be determined as a low cut-off frequency by comparing these 3 values, FLS, FLE, FLC. Okay, I will show you later. Okay, take a look here. This is the voltage divider with bypass RE configuration. Now we have RE and CE here, so it means the RE will be bypassed. Okay, first thing that you have to do is the AC equivalent network. Do you remember how to draw the AC equivalent network? Okay, it be like this. So you see, this is the beta RE, beta IB for the current here, and we have R out. So in this blue box, this is the RE model for the BJT. Okay, for this one. And then we have this parallel R1 and R2. If we come here, R1 and R2, sorry, this is another. And then the R out here is RC. Okay, RC. Then don't forget the current from here, IB, IC is equal to beta IB. Okay, the Z out here and Z in is here. Okay, next, once we get the AC equivalent circuit, now is the time to determine the effect of CS on the low frequency response. Means that I want to find FLS. Okay, so the network, okay, that you see from the AC equivalent network, okay, now we take a look at the input side, okay, during the input side. Okay, in this example, okay, actually there is another here, RS, and then we have VS here to complete, okay, to complete the circuit. Okay, for this one, for this example, this voltage divider has RS and VS here. So the input part is here. This is the input part. And the blue box, the system that you see from the next slide is here. Okay, so now we take a look from here. We have RS, we have VS. Okay, so it's like this. And don't forget, there is the capacitor here. Here should be, there is a capacitor here. The capacitor. Okay, the capacitor, it should be like this. Okay, so I draw again, sorry for this one. To complete the circuit, you have VS, RS, and then the capacitor. So you have R1, R2, beta RE, and this is the current, the R up, and RC, RC. Okay, so okay, this is the full AC equivalent circuit. Okay, then this is actually the R in, which is the Z in on the system. So for this circuit, you see that the impedance for this input, I see, okay, I call ZCS, okay, impedance for the CS here. So we have RS plus, okay, plus with the Z in or R in. Now the R in is Z in equal to R1 parallel with R2 and parallel with beta RE. Okay, then find the F here, FLS equal to the impedance and CS. Okay, don't forget to use CS here, okay, because we want FLS. So you get here, okay, this is the answer for the FLS. Okay, remember that FLS is at the input side. So which capacitor that we use? So CS, for the CS. Okay, next, because we have 3 capacitor, now we go to another capacitor, which is CC. Okay, so where is CC? CC is located at the output. Okay, output side of the amplifier. We have CC here, and this is just the Z up, RL, and V out. Okay, you see from this circuit, the R out equal to Z out. So what is the value for Z out? The Z out, okay, for the voltage divider, we get RC parallel with R out. And now the impedance at the CC is RL, okay, we plus with the R out. Okay, so we get this. Now we insert this impedance in the equation to get the FLC. So it become 1 over 2 pi multiply with RL plus R out and multiply with CC. See, don't use wrong capacitor. You must use this the capacitor here is CC. Okay, then we go to the last frequency, which is FLE. for the CE. Okay, CE is at the RE. Okay, so for this one, okay, we use the equation for the RE. Okay, because we know the RE now is a little bit complicated compared to the Z in and Z out. So this is derived, okay, from the AC equivalent circuit, and we get the RE. The value of RE is, okay, this is the RE from here, and parallel with the R prime, RS prime here, sorry, RS prime, divided by beta plus RE. Okay, this R prime we get from here. Okay, so what is RS prime? The RS prime is RS parallel with R1 and parallel with R2. This is because the circuit is voltage divider. Okay, if you are using a different circuit, okay, for example like fixed bias, you may have RB. Okay, so you only change this part. Okay, if you use another circuit, maybe RS parallel with RB, but for this voltage divider you have two input resistance, R1 and R2. Okay, then you get this, so use this impedance here, RE. For the FLE, we get this 1 over 2 pi RE CE. Okay, don't get confused. This RE is not same with this one, the capital E. Okay, for this one is RE, which is, we calculate this first. Okay, then we get this, and here, okay, means the RE is inside this equation. Okay,